If you want an AI to get smarter on its own, you face an impossible choice. Trap it in a rigid, narrow lab, or let it generate unguided garbage until it collapses. In the paper, Skill Self-Play, Pushing the Frontier of LLM Capability with Co-Evolving Skills by the Quinn Large Model Application Team at Alibaba, researchers actually solved this fundamental dilemma in LLM self-improvement. The core problem is the trade-off between reliable verification and task diversity. Current methods either restrict agents to narrow, verifiable domains, like code executors, or they use unguided generation that eventually degrades into synthetic noise. The researchers introduced SkillSP, a reinforcement learning framework where a proposer LLM, a solver LLM, and a skill controller all co-evolve. By using modular skills, which are programmatic bundles of rules, validators, and examples to guide task generation, the system maintains open-ended variety while ensuring rigorous verification. This approach completely avoids synthetic data collapse and achieves massive gains, including up to a 42.9-point jump in tool use. So welcome to this deep dive on AI Paperslop, where we summarize the latest AI and tech papers for technical practitioners.
Yeah, thanks. It's really great to be unpacking this one. I mean, the entire post-training paradigm for large language models is just shifting under our feet right now.
Right.
We are moving rapidly away from heavy manual data annotation where, humans write absolutely everything. And we're moving toward interaction-driven self-evolution. We're talking about multi-agent reinforcement learning, MARL, and self-play.
Yeah, but as we just laid out in the summary, ML engineers are hitting a massive wall when they try to actually implement this in the real world.
Oh, absolutely.
Because if you're an engineer trying to train an agent to improve itself, you essentially have to pick your poison. On one hand, you have environment-bound methods. So think of like game simulators or verified code pipelines.
Right, where the feedback is mathematically precise.
Exactly, it's precise.
Yeah.
But the model is trapped in extremely narrow operational boundaries. It only ever learns how to exist in that one specific simulator.
Exactly. And because of that limitation, the other extreme has become incredibly popular, which is unguided generation paired with like post hoc filtering. Right?
That's where the model generates just a vast open-ended array of tasks. And you just use schema checks or, majority voting at the very end to filter out the garbage. It broadens the coverage immensely.
But I've always thought of this like trying to train a world-class athlete. You can either put them on a treadmill in a lab, which is your environment-bound method. You perfectly measure their heart rate. Everything is verified. But that treadmill is never going to teach them the agility they need to play a real sport.
That's a great analogy.
Right. Or you drop them in a random forest. That is the unguided generation.
Yeah.
They might learn agility by dodging trees, but they also might just run off a cliff because there are absolutely no rules out there.
Yeah, that's a perfect way to visualize the tension. You need the agility of the random forest, but you really need the safety and metric tracking of the treadmill lab. The problem with dropping them in the forest and just using a post hoc filter is that a filter is just a passive sieve.
Yeah.
It doesn't tell the model how to construct a good task, it only tells it when it failed. So it's essentially just grading pass or fail without ever actually teaching the curriculum.
Precisely. And because it's just a passive sieve, residual errors inevitably slip through. So the model generates ill-posed tasks, or it realizes that certain really simple redundant templates always pass the filter. So it just exploits those over and over.
Oh, right. It finds the lazy way out.
Yeah, and over successive training iterations, as the model feeds on its own slightly flawed, highly repetitive outputs, those accumulated errors lead to synthetic data collapse. The training loop gets totally polluted with noise, and the model's performance just flatlines.
So the question this paper is really asking is, how do we get the agility of the forest with the safety of the lab? Like, how do we autonomously generate and verify diverse tasks without collapsing into narrow domains or chaotic noise? And their answer is to formalize this concept of a skill.
That is the bridge between the two extremes.
Okay, but I want to push back on this right away, though. Let's unpack what they mean by a skill. Because when I first read that, I thought, wait, isn't this just a fancy version of dynamic few-shot prompting or, RAG? We already inject examples and rules into our prompts to get better outputs. How is a skill in this framework any different from what practitioners are already doing every single day?
It's a vital distinction, so let's break it down. If you just stuff a massive history of raw execution trajectories into a single prompt, which is what a lot of standard self-play setups do, you get severe context bloat.
Right.
The model gets confused by too much raw data, and you actually dilute your structural control over what it generates next. But this paper defines a skill as a modular unit of procedural knowledge. It is a formal task pattern interface specifically constructed as a tuple.
A programmatic bundle.
Right. It contains routing metadata, procedural rules, generation hints, few-shot examples, executable validators, and historical usage statistics.
Oh, wow. So instead of giving the generation model a blank slate or just like a video of a past play, it's like giving a coach a modular playbook.
Yes.
The skill isn't just an example of what to do. It includes the rules of the game, which are the procedural rules. It includes tips on how to call the play, the generation hints, and crucially, it includes the exact referee criteria to know if the play succeeded, which are those executable validators.
Exactly. That coach's playbook analogy hits the nail on the head. It is proactive orchestration, not passive retrieval. The skill injects structural priors before the task is synthesized.
Okay.
It provides explicit programmatic mechanisms for verification after generation, and it tracks historical difficulty to govern the curriculum across multiple iterations. It's an active governing participant in the training loop. And this whole thing is managed by three distinct components. The proposer, which synthesizes the challenges, the solver, which executes and learns from them, and the controller, which manages the entire library of these playbooks.
Okay, so let's walk through the mechanics of that. The proposer has this playbook. How does it actually use it to build a training curriculum for the solver?
The proposer operates using two distinct generation streams. First, there's the skill stream. Here, the proposer is conditioned on a dynamically sampled skill from the library.
Okay.
This gives it those strong structural priors and rules we just talked about. But to ensure the model doesn't just get stuck exploiting known patterns, they run an exploration stream right alongside it. And this second stream is completely unguided.
Wait, if the exploration stream is unguided, aren't we just throwing them right back into the random forest? How do they ensure the tasks from both of these streams are actually valid before they get passed to the solver? Because we don't want to pollute the curriculum.
That is where the rigorous verification engine kicks in. For any generated task to be deemed valid, it has to pass three strict checks. First, global schema compliance. Like, does this output fundamentally look and parse like a real task? Second, contract validity. If the task was generated by the skill stream, it must pass the local executable Python validators defined inside that specific skill package.
The referee criteria.
Exactly. And third, they mandate what they call probe consistency.
Let's make sure that's clear for the listener. Probe consistency essentially means they test drive the task before they officially add it to the curriculum, right?
Yes, exactly.
So imagine the proposer generates a complex coding puzzle. The solver attempts to solve it 10 different times. If the solver gets 10 entirely different, equally plausible answers, it means the puzzle isn't actually hard, it's just poorly written and ambiguous. So it gets rejected.
That is exactly how it works. They draw 10 rollouts from the current solver policy. For the task to pass, those 10 rollouts must yield a unique majority answer that matches the reference answer the proposer originally defined. If it scatters into 10 different directions, the task is ill-posed and it's thrown out.
But wait, if the proposer is just trying to get the task to pass these validity checks, what stops it from just generating incredibly easy tasks? Because if the goal is just to make sure the solver gets it right, the proposer will just generate 2 plus 2 over and over.
You've just hit on the most elegant part of the paper. Generating a valid task isn't enough. It has to be a useful task. The researchers introduce a gated curriculum reward to optimize the proposer. The task must pass the binary validity filter we just discussed, and it must target the solver's learning frontier.
Okay, meaning what exactly?
Meaning the solver's empirical success rate on that specific task should be right around 50%.
Here is where it gets really interesting. That makes total sense. It's essentially targeting the AI version of the zone of proximal development. If the success rate is 100%, the task is trivial, no learning happens. If the success rate is 0%, the task is impossible, no learning happens.
Exactly. And think about how that 50% target brilliantly prevents reward hacking. A common setup in adversarial training is to reward the generator solely for making the solver fail. But if you do that, the generator eventually realizes the easiest way to get a reward is to invent broken tasks. It will ask the solver to translate a document into a language that doesn't exist. By forcing the proposer to aim for a 50% success rate, bounded by strict validity checks, you mathematically guarantee that the tasks are pushing the boundary of the solver's capabilities, but are undeniably solvable.
So the proposer generates these perfectly balanced 50% frontier tasks, and the solver trains on them. But here is the next logical problem. If the solver is actually learning from this curriculum, it's getting smarter.
Yep.
The tasks that were at a 50% success rate today are going to be at a 90% success rate tomorrow. The curriculum is going to go completely stale unless there is a mechanism to archive the easy stuff and invent harder stuff.
And that is exactly what the skill evolution controller does. It operates constantly in the background, creating a continuous bi-level co-evolutionary loop. It does three critical things to manage the skill library.
Okay, what are they?
First, it refines existing skills. It looks at execution trajectories that failed those validity checks we talked about, diagnoses the systematic failures, and updates the procedural rules inside the skill to patch the leaks.
So it basically edits the playbook to remove bad plays.
Yes. Second, it prunes saturated, obsolete skills. If a skill consistently yields tasks that the solver now finds trivial, meaning that 50% target reward drops too low, that skill is archived. This saves compute and forces the proposer to focus entirely on the shifting learning frontier. And third, it induces entirely new skills.
And it induces these from that unguided exploration stream we mentioned earlier, right? But how does that mechanically work? I think a lot of you listening are probably wondering how a raw text trace of a model exploring randomly magically becomes a programmatic tuple with executable Python validators.
It is a fascinating process. When the exploration stream happens to generate a valid, novel task that successfully pushes the 50% frontier, the controller steps in. It uses an LLM acting as a meta-analyzer. This analyzer takes the raw execution trace, runs integrity and lexical novelty checks on it to ensure it isn't just a duplicate of something we already have, and then it explicitly distills it. It prompts the model to extract the core procedural rule, synthesize a new local Python validator for it, write a few-shot example, and package it all into that formal tuple format to be added to the library.
Wow, it's literally automating the job of a machine learning data engineer. And as this library evolves, both the proposer and the solver are being updated continuously using GRPO, or Group Relative Policy Optimization.
Yes.
For those unfamiliar, GRPO is a highly efficient RL algorithm. Instead of relying on a massive, memory-heavy external critic model to evaluate an output, GRPO has the model generate a group of answers and rewards it based on how those answers compare to each other. It saves a ton of memory.
Right, and that memory saving is crucial because we are dealing with a notoriously heavy bi-level optimization problem here. The outer loop is optimizing the proposer and the skill library to constantly find that 50% learning frontier. Meanwhile, the inner loop is optimizing the solver using GRPO to actually master those tasks.
I have to play devil's advocate here regarding compute, though. We are talking about running dual generation streams. We are drawing 10 rollouts for every single task to check probe consistency. We're using LLMs as meta-analyzers to extract rules and write Python validators from scratch.
That sounds like a lot.
It sounds like an absolute compute bottleneck. If we are pruning skills and inducing new ones, how computationally heavy is this for the engineers listening? How can anyone actually run this without a supercomputer?
It's a very fair skepticism. It sounds overwhelming. But if you look at the paper's ablation studies on computational overhead, this skill library evolution, so the refinement, pruning, and induction, that accounts for only 6.5% of the end-to-end runtime.
Wait, really? Just 6.5%? That is surprisingly low. How did they optimize it to be that lightweight?
Because the LLM isn't retraining or doing heavy backpropagation during the induction phase. It's just doing inference to manage the library periodically. The vast majority of the compute is spent exactly where it should be on the actual curriculum construction, generating and probing the tasks, and the GRPO policy updates for the models themselves. The overhead of managing the skill abstraction is remarkably lightweight for the immense structural control it provides.
Okay, a 6.5% overhead is definitely palatable. But let's look at the actual benchmark scores. Because the system can be incredibly elegant in theory, but we have to ask, did the model actually learn new generalized capabilities, or did it just find a highly convoluted way to game its own system? What are the empirical results?
The results are massive, and they make sure to test this across multiple open source architectures to prove it wasn't a fluke. They used Qwen 3.4b Instruct, Ministral 3.8b, Ministral 3.14b, and Granite 4.13b.
That's a good spread.
Yeah, and they evaluated them on two distinct, highly complex families of tasks. Tool calling, using benchmarks like API Bank and BFCL, and logical reasoning, using ZebraLogic grid puzzles.
For context, ZebraLogic isn't just standard Q&A. It's essentially synthesizing and solving complex, multi-constraint logic puzzles.
Exactly. And across the board, Skill SP delivered breakthroughs. On the tool calling tasks, Minstrel 3.8b saw an absolute gain of 42.9 points over the base model.
Wow.
And on the logical reasoning tasks, Minstrel 3.14b saw a 12.0 point absolute gain.
The detail in the paper that really jumped out to me here was what happened to the standard unguided self-play baseline on those reasoning tasks. It completely failed. The unguided model totally stagnated.
Right, and it goes back to our discussion about the random forest. To improve at logical reasoning via self-play, you have to be able to generate valid logic puzzles to practice on. When left unguided, these base models simply couldn't independently synthesize valid, unique puzzles. They would hallucinate contradictory constraints.
Because if a puzzle has one constraint that says Alice sits next to Bob and another that says Alice sits across from Bob, the puzzle is mathematically unsolvable.
Precisely. And because the unguided models kept generating unsolvable puzzles, the solver was starved of meaningful learning signals. It was getting penalized for failing puzzles that were impossible to begin with. So its reasoning capabilities flatlined. But with Skill-SP, because the proposer had those structured skill playbooks guiding it, it generated valid, complex puzzles, which allowed the solver to actually learn.
You can clearly see the necessity of this co-evolution in their ablation studies, too. They asked, what happens if we turn parts of this engine off? If you freeze the proposer, meaning you just use the initial skill library and don't let the generator learn to make harder tasks via RL, performance drops. But what I found really fascinating was what happens when they froze the feedback solver.
Yes, understanding the role of the feedback solver is vital. The feedback solver is what the framework uses to probe the tasks and calculate that 50% learning frontier. If you freeze the solver, you sever that dynamic boundary tracking mechanism.
Right, so the signal gets warped.
Exactly. The proposer starts getting outdated difficulty signals. It thinks it is generating challenging tasks, but the actual training solver has already surpassed them. The performance degrades severely, dropping by 3 full points compared to the co-evolving system. Both policies absolutely must co-evolve.
The proposer has to adapt to synthesize harder tasks, and the feedback solver has to advance to provide accurate boundary evaluations. It's an arms race. But, a 40-point jump is huge, but benchmark scores can be deceptive. We have to look at the tasks the proposer is actually generating to prove it's doing what it claims. What does the data look like under the hood?
The diagnostics prove that this is actively steering the curriculum, not just filtering it. If you look at the mean solver success rate for tasks generated by the skill-routed stream, it hovers almost perfectly at 0.57 across all 5 training iterations. It stays locked onto that learning frontier.
Whereas the unguided exploration stream just drifts upward, right?
Exactly. The unguided tasks drift up to a 0.75 success rate. They become too easy, too fast, because without guidance, the proposer defaults to simple templates that the solver has already mastered. Furthermore, the researchers ran a PCA embedding analysis on the generated tasks.
For you listeners who might not visualize latent space clustering every day, a PCA analysis is basically taking the semantic content of these generated tasks and mapping them out on a graph. If all the dots clump together in one tiny corner, it means the model is just repeating the same type of task over and over.
Spot on. It's a way to check for mode collapse. And the visualizations showed that the unguided self-play tasks all clustered into narrow, highly redundant regions. But the Skill-SP tasks covered a massively broader semantic space. And to prove the library isn't just idling on a few dominant skills, they tracked the number of effective skills utilized over the 5 iterations.
Did it grow?
It grows steadily, reaching up to 46 effective skills. The model is continuously diversifying its own curriculum.
They highlight some really specific examples of these newly induced skills in the paper, and they are incredible to rate. For instance, in the tool calling domain, the controller autonomously induced something it labeled Skill 038. This was a skill where the model learned a specific pattern, basically, take a restaurant that it discovered in a previous turn of a simulated conversation, and dynamically turn that specific restaurant's details into a reservation ID for a subsequent API call.
Right.
It essentially learned multi-turn state tracking completely on its own.
And in the logical reasoning domain, they highlight Zebra Skill 022. This is a newly induced reasoning skill that represents a chain anchor bridge pattern.
Let's break down that jargon, because chain anchor bridge sounds like civil engineering. What did it actually learn to do?
It autonomously figured out how to generate and solve non-local positional dependencies in logic puzzles. So instead of just saying A is next to B, it realized, if I establish a fixed entity here, an anchor, and create a cross-attribute adjacency relation over there, a bridge, I can force the solver to make a complex multi-step deduction to connect them.
Wow.
For example, The person in the red hat sits 2 seats away from the person who ordered coffee. It's synthesizing complex relational logic.
It is literally inventing new logical paradigms to test itself with. It finds a tiny spark of a good idea in that random exploration stream, and instead of losing it in the noise, the controller snaps it up, formalizes it into a verifiable Python validator, and forces the proposer to master generating it. The fact that the system automatically distills raw exploration into reusable, verifiable structural priors is just a massive leap forward.
It really is. What we are seeing here is that co-evolving skills successfully bridge the gap between structured verification and open-ended exploration. The skill library acts as a dynamic training time scaffold. It completely resolves the tension between wanting the perfect mathematical feedback of a simulated lab and the broad diversity of the open-ended forest.
So what does this all mean for you, the practitioner? Well, it means the bottleneck of synthetic data collapse in post-training might just have a viable solution. But I want to leave you with a final forward-looking thought that wasn't explicitly covered in the paper, but is heavily implied by this architecture. Since these induced skill libraries are entirely modular, they're essentially just text-based tuples of rules, hints, and validators. Could a massive state-of-the-art frontier model run skill SP for a month, build a flawless, highly complex skill library of thousands of intricate reasoning patterns, and then simply hand that entire library down to a tiny 1 billion parameter edge device model to perfectly bootstrap its training from scratch?
A distilled curriculum of pure, verifiable reasoning constraints mapped out by a frontier model, executed by an edge model. The implications for democratizing alignment and training highly capable small models are massive.
Definitely something to mull over as you look at your own domain-specific reinforcement learning pipelines. How might you implement automated skill induction to keep your models relentlessly targeting the learning frontier? Thanks for joining us for this deep dive on AI paper slop